Hi everyone, I'm Ritwika and today I'm going to talk about the CyPhyHouse toolchain for programming, simulation, and deployment of heterogeneous mobile robotic systems. To give you a clear idea of the type of applications our toolchain is intended towards solving, let me start with an example of a distributed task allocation problem. Suppose we're given a set of tasks specified by their locations and a set of robots which may be heterogeneous, say a mix of ground vehicles and quadcopters. These robots are required to collaboratively visit each of the task locations exactly once while maintaining a safe distance from each other. So what would a natural approach to solving this problem look like? When each robot starts the application, it looks for an available task. On finding such a task, the robot checks whether it has a clear path to it. If not, it looks for another available task. If this task has a clear path to it, then it shares the path to this task with the other robots and follows the path. This is how tasks are assigned. Upon reaching the location of the task is marked complete, and the whole process repeats until there are no more tasks. This is a fairly straightforward design. So what are the problems with implementing this application? The problem is that there are multiple areas of expertise that are required for implementation. Checking the availability of a task in a shared list of tasks among robots requires expertise in distributed coordination, including concepts of mutual exclusion. Finding a clear path to the task requires sensing and path planning, and sharing that path to other robots requires communication between robots through networking. To simplify the process of programming distributed robotics applications, and to mitigate the necessity of having all the aforementioned areas of expertise at one's disposal, we designed CyPhyHouse. It's a toolchain which enables programming, testing, debugging, and deployment of multi-robot systems. It includes a high-level language called Quad with the Quad language compiler. Applications written in Quad can be deployed or simulated through a middleware. Let's see how the design of the task application gets implemented in the CyPhyHouse toolchain. The code for the task application is about 50 lines. We designed the Quad language with features that abstract away standard but tedious platform-specific control functionality and difficult and error-prone coordination across distributed and possibly heterogeneous robots. For this task application, robots coordinate between each other through shared variables with different permissions for reads and writes. The list of tasks with locations and status of each task and the currently planned path of each robot are shared using such shared variables. The user doesn't worry about communication protocols and mutual exclusion. In our implementation and experiments, we used UDP-based messaging over Wi-Fi. Each shared memory update is essentially an update message that the robots broadcast over Wi-Fi. We have certain assumptions about the consistency and the reliability of the shared memory, such as a single distributed Quad application runs on a single network node and there is negligible packet loss. Also, this application requires mutual exclusion, which we implement using a lock-based mechanism. The other major language features which abstract away low-level platform-dependent control from the programmer are sensor and actuator variables. These are used in the task application to check the robot's current location, to set the path of each robot, and to check whether it's reached the current task location. Each platform, be it ground vehicle or quadcopter, requires an implementation of how reads and writes occur on the actuator and sensor variables in the middleware. For instance, in the task application, we use sensors for position of the robots, which require subscribing to the correct ROS topics for positioning. The application developer does not need to know the details of these implementation. Another functionality that this enables is plugging and playing different path planners for robot motion, including RRT, A-star, D-star, probabilistic roadmap, and other popular path planners. We have implemented several RRT-based path planners for use with the task application with varying results. These plug-and-play features, shared memory, and sensor actuator variables make the same code applicable across a variety of platforms. So we aimed for portability with the code, and simply changing configuration files allows the same code to be tested on various configurations on our simulator. In this video, we show a simulation of the task application on 5 quadcopters and 3 cars performing the task application. The gray circles are unassigned tasks. They turn red when they're assigned and they turn green when they're completed. Here we show a deployment of the same code on heterogeneous vehicles. This setup has 2 F-110 cars and 2 quadcopters with the same legend as the previous video. The gray circles are unassigned tasks, the red circles are assigned tasks, and they turn green when the task has been completed. The bottom right corner of this slide shows a visualization of this execution in the gazebo environment. As I mentioned earlier, we use configuration files to allow users to deploy and simulate the same code on various configurations without changing or recompiling the code. A configuration file includes information about the robot's name, the CyPhyHouse implementations used for actuators and sensors, ROS topic info, and system information such as number of robots. These are used both for simulation as well as deployment. CyPhyHouse comes with a high-fidelity simulator, including a gazebo environment and the same communication interface as the hardware. The simulator runs the compiled quad applications directly with one instance for each robot. The same application code can be tested with multiple scenarios by simply changing the configuration file. We implemented several other applications in quad. This video shows a formation flight application which includes about 5 lines of quad code and forms a rhombus in 3D. This next video is of a collaborative mapping application where 2 robots with LiDAR sense static obstacles individually and share their local maps to compute a shared map of the given space. The green portion of the map is unoccupied and the yellow are the obstacles as detected. There is a lot of related work in this problem space. Prominently, the Robotarium project allows remote deployment of distributed MATLAB robotic applications. One major feature of the CyPhyHouse toolchain is that the language design and formalization, which is not part of this paper, allowed us to build a verification and validation component. This is not supported by most other projects in this space. The Drona project explores the verification and validation problem space as well, but to our knowledge, they do not support heterogeneous or indeed general robots as the CyPhyHouse toolchain does. In conclusion, CyPhyHouse toolchain with its high-level programming language abstracts away low-level platform-specific control and platform-independent coordination details from the users. CyPhyHouse is intended for interfacing with and complementing existing tools which roboticists commonly use, like ROS. We believe that it provides easy integrations with popular platforms by almost any user. And our experience suggests that the quad, language, and compiler can enable users to develop and run distributed robotics applications in a hardware-independent fashion. Quad programs can be ported across platforms automatically with minimal effort from the application programmer, and our high-fidelity simulator can provide a valuable testing and debugging environment. Before I end, I have a few acknowledgements. This work is supported by an NSF infrastructure grant. We'd like to thank John Hart of the Coordinated Science Lab at the University of Illinois for facilitating the experiments. And finally, Sasha Misailovic for his input on the language semantics and the formal verification approach of quad programs. Thank you for watching this presentation. Please look us up at our website cyphyhouse.github.io and please feel free to reach out with any questions.